Hello, my name is Mikko Muilu. I'm a project researcher from the University of Jyväskylä, Finland. I'm working on an Erasmus Plus project, Computational Thinking and Acting. It's an international project aiming to help teachers on teaching computational thinking by giving them tools and support. My co-authors of this paper are Saana Mehtälä and Kati Clements from the University of Jyväskylä, Finland. Professor Jan Pawlowski and Martin Idzik from Ruhr-West Högskolan, Bothrup, Germany, Michael Pilv from Miksike in Tartu, Estonia, and Dimitra Kopoulou from Elino-Germaniki Agogi, a private school outside Athens, Greece. I am here to present our paper, What are the Barriers for Teaching Computational Thinking?, which is published in the INSEAD 2021 proceedings. The paper presents a survey study of teachers from Estonia, Finland, Germany and Greece, and the problems and barriers they face with computational thinking and teaching it. We also present some solutions that the interviewed teachers mentioned to overcome these barriers. What does computational thinking mean, you might ask? Computational thinking, or CT, might sound like the familiar term Information Communication Technology, or ICT. However, computational thinking does not mean the technology itself, but more the logic of how technologies like computers, smartphones and robots can function and solve problems. Some countries, like Greece schools, prefer the term algorithmic thinking. Although computational thinking is becoming more and more a required skill for future jobs, there is still no common curricula, nor common teaching practices for computational thinking in the different countries around Europe. Let's look at an example of teaching computational thinking for third graders. Third graders can play human robot, where one student is a robot and is taking written instructions from another student. They quickly realize that common language and clear terms are crucial for unambiguous instructions. The need for common language and terms become understandable. The order of commands is also important. You can't wash your hands under the faucet if you haven't opened the faucet first. Sixth graders can grasp abstractions more readily and can be given algorithmic tasks. For example, paired students can try to guess what number the other one is thinking between 1 and 100. The other student can answer only yes and no. After trying this out for some time, they have a pretty good idea of how slow just guessing is, and they start to use "is it bigger than" type of mass elimination questions. When you present the idea of binary search, many students grasp it right away. The potency of it is mind-blowing and harder to really understand without examples. Students can try to guess how many answers it would take to find a number between 1 and 100, it's 7, a number between 1 and 1,000, it's 10, a number between 1 and 10,000, it's 14. A number between 1 and 1 million would be found in just 20 questions. After a tangible example like this, the power of good algorithms can be intermediated. After a tangible example like this, the power of good algorithms can be intermediated. Also, sorting algorithms can be conveyed as play. The true power of different sorting algorithms comes, of course, only after millions of items are sorted. But the ideas can be portrayed with tens of beads or tiles that can be ordered on students' desks. Development in computational thinking leads to more profound applications and implementations. When students have a basic understanding of the logic of coding, they can start to make their own inventions. Some teachers are creating sumo championships, competitions with pre-programmed Lego robots. Students perceive this as playing, not as studying. They reprogram robots and want more rematches than there is time for. Teaching basic computational thinking isn't always dependent on resources. Teachers can use games, play and imagination quite far before computers are needed. Where can teachers get the ideas for their classes? One solution is our project website, cota-project.eu. Let's talk a moment about our project's Kota's activities and ideas. Kota's goal is to develop and validate new learning and teaching ICT solutions in computational thinking and problem solving in primary schools. Kota will explore the concept of physical computing and provide open learning activities for programming including teacher materials and teacher training. Kota will also develop scenarios for integrating programming into different subjects and competence framework of physical computing linked to existing national curricula in Finland, Estonia, Germany and Greece. The gathered and developed learning scenarios and resources will be free of charge and available for everyone. We are constantly adding more learning scenarios to our website. You can search for learning scenarios in English, Estonian, Finnish, German and Greek. In 2022, we will have a collection of at least 40 learning scenarios in all these 5 languages. We hope to get an active user base that would use the learning scenarios, modify them and maybe create some of their own too. This way, we will have an open library of learning scenarios on computational thinking where teachers can go and look for exactly what they need. But let's get back to our paper. In our study, we wanted to find out what we can do for teachers and schools in terms of teaching computational thinking. Firstly, we conducted a literature review on previous studies and based on that interviewed 41 teachers from Estonia, Finland, Germany and Greece. We found 3 categories of barriers teaching computational thinking and you can see them here. Personal barriers consists of personal barriers of teachers and students. Institutional barriers include barriers that are dependent on the school or institution. The last category is technological barriers. In this next figure, you can see how the different categories were presented in different countries. The profiles look roughly similar. Let's look at them in more detail. Here we can see that the change resistance is mentioned only in Finland and Germany. Lack of teacher education seems to be high in every country. Teacher and student motivation are mentioned a couple of times. Interviewed middle school teachers mentioned the heterogeneity of the students they receive from primary schools. Lack of time is a great institutional barrier. This includes time to practice computational thinking with students, but also preparing the classes. The allocated subject was presented as a solution for the time barrier. Well-made material would also save teachers' time. Lack of staff and large group sizes are solid institutional problems. Technological barriers consists solely of lack of resources. This could also be seen as an institutional problem. As our project is international, we can provide help for many teachers and therefore we can tackle the main problems risen in the interviews. So far, we have created educational materials to meet the barrier lack of material, but we can clearly see the need for teacher education to support the use of these materials. To summarize, in this study we discovered there is a need for the materials we are gathering and creating for the Kota project, but there's also a need for teacher education resources in which we intend to overcome by creating training still within the project duration. Clear roadmaps are needed for the students and teachers so everyone is on the same page when they are moving to the next level. Our study should also be read by the institutional leaders to serve better their staff and students. Thank you for your attention and interest in this topic. You're welcome to contact me or our project if you wish to know more, contribute or just to say hello. Go to our website to explore some learning scenarios and maybe test them in your own classrooms once COVID-19 allows contact teaching again. Enjoy the rest of the conference. I know I will. Goodbye.